Hello and welcome to the Kopeopeo Canal Remediation Project. What do the numbers mean? Presentation by Andrew Colrush and Matt James from GHD. Up front, we wanted to address questions that were important to the community. So we've brainstormed a few on the slide, and we also received one from the community liaison group around who signs off the soil validation report at the end of the project.
There are a number of guidelines that the New Zealand MFE has put together for the assessment and management of contaminated sites. They all have the basis in the document called the Methodology for Deriving Standards for Contaminants in Soil to Protect Human Health. That document outlines the background behind how the MFE came up with investigation levels. It includes also the reference materials such as US EPA, Canada, the Canadian Ministry for Environment, Australian government agencies, as well as the World Health Organization. The values are based on a lot of conservative assumptions, taking into account statistics on general population, eating habits, drinking habits, etc. And they're all used to come up with soil investigation levels. So in establishing soil investigation levels, there are a series of pathways, or these are the ways in which people could actually be exposed to chemicals in soil. They include soil ingestion, which is actually eating soil or actually coming into contact with soil which you might swallow. Product consumption, so that's food that is grown in backyards, and that might also be come into contact with contaminated soil. Dermal exposure, which is soil that actually comes into contact with skin, and then the way in which that chemical might absorb through the skin. And there are again various assumptions made regarding the amount of skin that could be come into contact, the ways in which the chemicals can actually migrate through the skin. Inhalation of particulates, so that's when you just breathe chemicals that might be in either soils or in the atmosphere that are released from the soils that might be contaminated. And there's also the inhalation of volatiles, which are, say, for example, the fumes you might smell at a service station when you're filling up your car. So from these particular pathways, each pathway there's a number that's assigned for that particular chemical, and they are all added together to come up with a final soil guideline value, or an SGV. So generally when you're assessing a site, you will take samples and you'll send those samples to a laboratory. The laboratory analysis will be then evaluated, and then there will be a comparison of those laboratory data to the soil guideline values. So because the soil guideline values are very conservative, if the concentrations that you have measured in your soil are less than the soil guideline values, there is no further need to do any assessment, and the site would be considered to be suitable or safe to use for that particular purpose. So in relation to these soil guideline values, there are 5 standard scenarios that have been established in New Zealand for various land uses, and they include the rural residential with up to 25% of homegrown produce. There is standard residential, which is more suited to large industrial, larger urbanised areas, and that's 10% of your daily produce comes from your own garden. High density residential, which will be large flats, etc., where there's very limited soil access. Recreational land use, which will be parks and gardens and football fields, etc. And then you have the commercial land use, which is your standard working area, where the exposure to soils will be very minimal. Right, the standard investigation levels that have been established by the MFE also include dioxins. Of the dioxins, there are 210 possible congeners, and 17 of which have toxicological concern. They don't occur as pure compounds. There's generally a mixture of compounds. And the total toxicity, the different congeners have different degrees of toxicity. And they're all related to 2378 TCDD, which is assigned a toxicity equivalent factor of 1, and that is considered to be the most toxic. The other 16 have toxicity equivalent factors that are less than 0.5 or even lower, even as low as 0.0001. So what is undertaken is those 17 congeners are tested or analysed. There are results that are provided of the actual raw concentrations of those congeners in the sample, and each of those congeners is multiplied by the toxicity equivalent factor. Those toxicity equivalent factors multiplied by the actual concentrations are then summed to come up with a TEQ, or toxicity equivalent. The toxicity equivalent is expressed in three particular ways. The laboratory reports results that are called ITEQ high, ITEQ medium, and ITEQ low. There's also a difference in the way in which the toxicity equivalent factors have been established. The one was prepared by called the International, which is the ITEQ, and there's also then the WHO, which is the World Health Organization toxicity equivalent factors. Those, the former, the ITEQ, are slightly more conservative, and they are the numbers that are used in calculating the concentrations of dioxin that have been found in the Kopeopeo canal. So by way of background, the MFE has established standard dioxin values for those 5 scenarios I was talking about: the rural residential, the standard residential, the commercial, the recreation, and the high density residential. These are the standard values. These are based on a number of scenarios that are commonly occurring in the community. And as you can see there, they range from 120 to 1400 picograms per gram TEQ. For the Kopeopeo site, the scenario or the way in which the people might be exposed to the dioxins in the canal is much different. And as a result, there was a risk assessment undertaken following the MFE guidelines to come up with site-specific values or cleanup levels or targets for the Kopeopeo canal. So Toxconsult was engaged in 2013 to prepare this site-specific risk assessment for the sediments in the Kopeopeo canal. That took into account there were a series of eels that were caught along the canal, and there were also sediment samples which were collected in the same areas in which the eels were collected. The weight of the eels was measured. The samples of the skin and the flesh were taken, and then they were analysed for the presence of dioxin. The resultant estimate that was undertaken based on standard equations for how these chemicals might be consumed or be taken up by people who eat eel resulted in a potential dioxin uptake of 0.55 to 0.78 kilograms per day. Now that's just a kilograms per day, and that's then converted then to a value based on a 70 kilogram person to work out how much someone could consume at a regular sitting. It also took into account the number of eels that might be eaten on average in a week, and the average was about three servings of eel per week. Based on the potential uptake that people would consume per sitting, as well as the background, and the background level is a value that has been established by the New Zealand government with the 0.33. There was a combined intake based on eating eels, as well as your standard background. There was a combined intake of 0.88 to 1.11 kilograms per day. Now that was the upper range of that was slightly in excess of the value established for the MFE, and that was then used as a guide, or the values were used as a guide to then back calculate what the concentrations of sediments could actually realise in that particular ingestion of eel. There were 3 site-specific exposure scenarios that included consumption of eel, absorption of dioxin-contaminated sediments during the eeling, and dermal absorption during swimming. The latter two were regarded as, in the risk assessment, as being not significant at all in relation to the exposure. So the prime exposure route for dioxins in the canal was the eating of eel. So based on the body weight of the average person that eats eels, the consumption rates of the eels, as well as sediment data, they back calculated the concentration of sediments that could actually result in an unacceptable exposure of eating eels to a range of 64 to 92 picograms per gram, and that was rounded down to 60 picograms per gram, which is the remediation target for the Kopeopeo canal.
So now I just want to go through the dredging, validation and results process from start to finish. So we'll start with the dredging. So we have the cross section of the canal before dredging with 1 to 2 meters of target material in the base. After dredging, we're left with, on average, 0 to 30 millimeters of residual resettled target material in the base of the canal over the natural base material, which is often silts, clays or sands. A validation sample is taken of the top 100 mils of the base of the canal. So this makes up that 0 to 30 mils of resettled, and then somewhere in the sort of 70 to 100 mils of natural base material. This is put into a jar and then sent away for laboratory analysis. We now have 2 examples of the validation cores that are taken from the canal. The first one shown here is a pass. So this got a result of 23 picograms per gram, which is below the validation target of 60. As we look at the core, we can see a very thin layer of sort of 5 mils of resettled target on the top. It's a bit difficult to see in the left-hand photo, but it is just that small layer on top of the grey natural sands. So this core is laid out, as you can see in the photo at the bottom, and then the top 100 mils of the sample is taken and put into a jar and sent away. When you compare this sample here with the previous one, it's pretty obvious that here you have a thick layer of black target material. If you look at the bottom photo, you can see really clearly that boundary between target material and the natural base of the canal. So if you were to take the top 100 mils here, you are getting predominantly target material going into that jar and going away for the lab. And this is reflected in the lab result that came back from the sample of 990 picograms, so 15 times your target level. This particular core was taken near the outfall from the Whakatane mill, so it's near the source of the contamination and where it's expected to be at its highest. This just shows the raw lab results that come back from those samples that are sent away. So you have all the congeners broken down, and then the ITEQ totals at the base, which is what we use, the ITEQ upper bound, which is what we use to compare against the remedial targets. So in this example, all of the congeners have added up to a ITEQ upper bound of 47. So that is what gets compared against the 60 picogram target level. So for this particular result, KC112A, taken on the 1st of May, it is a pass. So if we remember back to the previous slide where we had KC112A with 47 picograms per gram, we can see it here represented visually on the map. To the left of the section of the canal is KC112A. Now the bar graph at the bottom is a visual representation of the results, and the blue line is the limit of reporting of the lab. So that is 20, and that is the lowest result we can get using this lab method. The 60 red line is the remedial target. So as you can see, all of these results are well below the remedial target.
Just to outline the way in which the data is evaluated, the resource consent has stipulation that the results of the testing should be compared to a 95% upper confidence level, and that value, that upper confidence level value, has to be below the 60 picograms per gram. This diagram shows what is meant by an upper confidence level. You put all your data into a particular equation, and the equations are based on US EPA methods. The data is put into those equations and it comes up with a range of results, and if they're all normally distributed, as you can see in this graph, and it shows you a nice sort of peak where all the chemicals, all the results will fall within, the majority of those results will fall within the two ends of the graph. So what it states there is that the results for 95% of samples are likely to fall within that particular range of results. So you can have some results, as you will see, as you may have will see in some of the information on the website, that might exceed that 60 picograms per gram value, but from a statistical point of view, they're considered to be of the same data set, and there's some sort of acceptable variability. So you sometimes might see 60s or 1s or 62s or maybe up to 70 or so, but from an averaging out based on the confidence level, they are considered to be the same population.
So here we have a visual representation in the form of a conceptual site model of the canal before the remediation was undertaken. So here we want to stress the source, pathway and receptors. So the source is the dioxin, that's the source of the contaminant. So here we have the dioxin in the sediment at the base of the canal, and we also have some dioxin on the contaminated stop banks along the canal. So the stop bank, that we then look at the pathway. So that's the way that the contaminant or the source can get into the receptor being humans. So the pathways here, we have the cow eating off the contaminated stop bank. We have dermal contact from people using the stop banks, launching kayaks, fishing, swimming, and we also have the primary driver, which is eel being ingested by the receptor as people go and catch eel that has been living in the dioxin sediment. Worth taking note that the contaminated stop bank levels that we've seen along the canal are below 330 picograms, the highest being along the gateway section of the Kopeopeo Canal. This is below the Ministry for Environment recreational guideline level of 600. The 600 is based on people using sports fields to play rugby and things like that. So that's sort of a bit of a context on the risk from the contaminated stop banks, which we'll cover further in the next slide. So this is the conceptual site model post-remediation, and there's some pretty important changes here. So if we look first off at that contaminated stop bank, so the fence stops the cows accessing the bank, and that stops a pathway. Okay, it stops contaminant going into the cows as they're eating off the stop bank. There's still dermal contact from people using the stop bank to launch kayaks and stuff, but that's a recreational activity. The stop banks are below the recreational guidelines, so for a standard recreational activity, people launching kayaks, walking along the stop banks, the risk is deemed acceptable by MFE. So as we look at where the dioxin sediment was in the canal, that has been removed and it is now placed in the geobag to the right hand side of the model, and it is contained in the bag, it is in a bund, and it's surrounded by clean fill material. If we look at the receptor, who is the human standing on top of this area, there is no pathway for that contaminant to get to the receptor. If we also look at the human sitting fishing on the stop bank, again there is a pathway from the eel there, but there's no source. The source has been removed, so the contaminant is not getting to the human. For the final slide, we just wanted to bring it back to the questions that were asked at the start of the presentation, were presented, and we also just want to touch on a few questions that were raised during the community liaison group meeting by members of the community. So both Andrew and I are going to just sort of present on our thoughts and answer questions as we can think of them. So to start with the anything above zero, and why is zero not the target, or why are we not seeing zero? So do you have a natural amount of dioxin present in the environment anyway, so we're never going to hit zero, combined with the fact that the lab can't report zero. So for the results we're seeing, the limit of reporting that the lab can go down to confidently is 20. So if the lab was able to go lower than 20, those 20s may turn into 2s, but for the purpose of the remedial target being 60, as long as it's below 60, it's okay. How did we end up with the 60 picograms as the remedial target? This was based on the site-specific investigation. The 60 picograms is lower than any of the guidelines from the MFE for the other normal land uses, and this is driven by the eel consumption rates from the local community. We also had a question on sign-off of the validation at the end of the project, and this is done, the reporting will be sent to the IM for review and the consent authority for sign-off. This will then be passed on to community, Ministry for Environment, anyone who wants to read that. Was that everything?
I just wanted to add one more thing about the concept of zero. Not only dioxins, but any other chemical that is tested by any other laboratory can never actually attain zero. So the laboratory techniques that are used for this project and for any other projects for sampling dioxin are as conservative and as low as you can go. And the concentrations that were generally being found in the validation samples are pretty close to that 20 target, that 20 level of reporting. I think there's a lot of confidence that there's going to be a good result following all the remedial works.